There is a region thought to surround the entire solar system, so vast that even light could take more than a year to cross its farthest part. But the strange thing is that this region does not appear in any clear image. There is no glowing boundary. There is no visible shell. No object at its outermost edge has ever been directly confirmed. The Oort Cloud exists in science in a different way. It is not like Mars, where a spacecraft can photograph the surface. It is not like Jupiter, where telescopes can track the atmosphere. It is also not like the Kuiper Belt, where many distant objects have been discovered one by one. This region appears through the traces of visitors that only show themselves when they leave the darkness. They are long-period comets. They plunge into the inner solar system from very different directions, brighten near the Sun, and then disappear again onto orbits so wide that no human lifetime could wait for them to return. If we have never seen where they begin, why does science still believe that place exists? The answer begins with a realization that seems very simple. The solar system does not end at the last planet. In familiar maps, the solar system often looks very neat. The Sun sits at the center. The planets line up in clear orbits. Mercury, Venus, Earth, Mars, then the giant planets, and finally Neptune in the cold, distant region. That way of drawing helps people easily picture their place in space, but it also quietly creates a misunderstanding. It makes the solar system look like a place with a clear outer edge, as if everything ends once the last planet is passed. In real space, there is no neat boundary like that. Neptune orbits the Sun at about 30 astronomical units, roughly 30 times farther away than Earth. There, sunlight has already become much weaker, but this planet is still only the last major landmark in the familiar planetary region. It is not the end of the entire system. Beyond Neptune's orbit, there are still icy objects, extended paths, and leftover remnants from the time when the solar system was being built. The clearest layer after Neptune is the Kuiper Belt. Pluto lies within that region, along with many small bodies that humans have only begun to identify in recent decades. The Kuiper Belt is often described as extending to about 50 astronomical units. That number is already very far when seen from Earth, but in the true map of the outer region, it is still not the farthest part. Telescopes can still detect some small points of light in this region, measure their motion, and place them into a structure like a broad disk around the region beyond Neptune. Farther out, the solar system no longer has a single kind of boundary. The heliopause is often considered a major landmark, where the solar wind weakens against the interstellar environment. It is the region where the stream of particles emitted by the Sun no longer dominates the surrounding space as it once did. If the Sun is seen as blowing a giant bubble into the galaxy, the heliopause lies near the outer edge of that bubble, but that is the edge of the solar wind, not the final edge of gravity. The farther out one goes, the word edge no longer works the way it does on a map. For the planets, Neptune seems like the final marker. For icy objects that have been directly discovered, the Kuiper Belt extends the map by another layer. For plasma and the solar wind, the heliopause marks where the breath of the Sun begins to give way to the space between stars. But gravity does not stop at a signpost. It grows weaker, and other forces begin to interfere, but it can still hold small pieces of ice on orbits so wide that they almost exceed human intuition. At distances of thousands of astronomical units, the Sun is no longer the dominant source of light in the sky. From there, looking inward, the central star would be only a prominent point of light among other background stars. If small pieces of ice and rock are drifting in that region, they would not reveal themselves the way planets or dwarf planets do. They are too dark, too small, and too far away. They do not create a boundary for telescopes to catch, do not arrange themselves into a dense belt, and do not emit strong signals. They may be separated from one another by enormous distances, cold and almost absolutely silent. The Oort Cloud is placed in that hard-to-see region. It is not like a wall surrounding the solar system, and it is not like a dense shell that could be photographed from the outside. It is a region inferred from gravity and motion, where the sun still has enough strength to hold icy objects, but is no longer close enough to make them easy to reveal through light. There, the solar system does not disappear. It only gradually loses the familiar signs that human eyes and telescopes usually rely on. A region like that is not easy to prove by looking directly at it. If those objects are lying very far out there, most of them would be too dark, too small, and too slow to appear clearly. They only enter the story when an orbit is disturbed, when a piece of ice from the distant region begins to fall back toward the sun, and after a very long journey, appears in the bright region, in a form humans have seen for thousands of years. That form is a comet. But a comet, when it is still very far from the sun, does not look like the familiar image in the sky. There is no long, bright tail. There is no hazy envelope of gas around it. There is no brilliant appearance like the photographs usually taken after a comet has entered the inner solar system. For most of its journey, a comet is only a frozen mass of ice, dust, and rock, drifting through darkness on an orbit so wide that it almost lies beyond ordinary human perception. Far from the sun, a comet is almost silent. The light is too weak to make the ice on its surface evaporate strongly. That small object does not create a tail to introduce itself. If there is no change in its orbit, most icy fragments like that can continue to remain outside the observable region for an enormous length of time. Cold, dark, and almost leaving no sign at all. Everything changes only when a comet begins to fall inward. As it moves closer to the sun, its surface heats up. Volatile substances escape from the ice, carrying fine dust with them and forming a hazy layer of gas around the nucleus, called the coma. The solar, wind, and radiation pressure continue to push that material behind it, creating the bright tail that humans had seen long before they knew where comets truly came from. But the tail is not the most important clue. It is only the moment when the comet becomes easy to see. The more valuable thing lies in the motion of that object. A comet entering the inner solar system is like a witness appearing late in an old case. It does not carry a map of where it began, but its path preserves the trace of a very distant source. With short-period comets, the story is usually closer. Many objects of this type are linked to the region beyond Neptune, where the Kuiper Belt and the scattered disk can supply bodies that are disturbed and then fall inward. Those orbits still belong to a part of the solar system that is easier to imagine, close to the plane in which the planets are moving around the sun. Long-period comets are harder to handle. They can take more than 200 years to complete one orbit. Some comets pass through the inner solar system only once in the entire history of human observation. They brighten for a short time, leave behind a few measurements, a few images, a few calculated paths, and then disappear onto an orbit so wide that their next return may lie beyond every memory of the present civilization. Their appearance creates a very specific problem. Comets cannot keep passing near the Sun forever without changing. Each close approach makes them lose material. Ice evaporates. Dust is pulled away. The surface is eroded, cracked, and sometimes the comet's nucleus itself breaks apart. After enough passages through the hot region, a comet can weaken or no longer exist as it once did. In a solar system more than 4 billion years old, the source of long-period comets cannot simply be an old group of objects repeating the same journey forever. What is difficult to ignore is that they still appear. Not all comets come from the same place, and not every long orbit tells a simple story. But the existence of long-period comets forces science to consider a very distant reservoir, where icy objects can remain still for an extremely long time, far enough away to avoid being continuously eroded by the Sun, but still weakly held by the Sun's gravity. That reservoir does not appear as a bright region in the sky. It only reveals itself when a piece of ice is awakened from a distant orbit, falls inward, and brightens under sunlight. Each long-period comet is a fragile trace from the dark region. But when many paths are measured, compared with one another, and placed on the same map, the problem is no longer in the bright tail that humans see, but in the path the comet leaves behind after that light fades. That path is what makes long-period comets different. A bright tail can draw attention for a few weeks, but the comet's orbit is the part that remains in the scientific record. When a comet passes through the inner solar system, observers can measure its position night after night, track how it shifts against the background stars, and then reconstruct the path of that object around the Sun. From a faint point of light, a curve begins to appear. That curve shows how fast the object is moving, which direction it came from, how much it is tilted compared with the orbital plane of the planets, and how far away it may have fallen in from. For some comets, the orbit does not resemble neat paths around the region beyond Neptune. They stretch deep into the dark region, much farther than the part of the map that has been filled in by directly observed objects. The strange point lies in the direction they come from. If the source of long-period comets were only a flat belt like the Kuiper region, many orbits would tend to stay closer to the shared plane of the planets. But the data does not follow that simple direction. Some comets enter from very steep angles. Some almost plunge down from above the planetary plane. Others rise up from below. Those paths do not draw the image of a thin disk. They suggest a source surrounding the solar system from many sides. This is where the idea of the Oort Cloud begins to carry weight. Not because anyone has seen a cloud of ice at the far edge. Not because a telescope has photographed a faint boundary surrounding the Sun. This idea becomes stronger because the orbits of long-period comets need a reasonable place of origin, distant enough for icy objects to survive for a very long time, broad enough not to be forced into the plane of the planets, and sparse enough to almost never reveal itself through light. In 1950, Jan Oort looked at that problem in the way of a dynamical astronomer. He did not need a photograph of the source region. He had something else. Orbits. They were like footprints left in snow after the traveler had disappeared from the frame. No one saw where the journey began, but the direction, curvature, and speed could tell part of the story. From long-period comets, Oort proposed that there must be a very distant reservoir of icy objects, a source that could continue sending comets into the inner region after billions of years. That kind of reasoning is not like discovering a new planet through photographs. It is closer to reconstructing a scene from scattered pieces of evidence. Each comet provides only a small slice. A single orbit can be disturbed by many factors. But when many orbits together show very long paths, arrival directions that are not concentrated in a single plane, and periods far beyond ordinary observation time, the emptiness out there begins to take shape in mathematics before it takes shape in images. What must be kept in mind is that the Oort Cloud does not become an object that has been seen simply because this model is convincing. Science does not say that there is already a clear photograph of that region. Science says that if the paths of long-period comets are taken seriously, a distant and widely distributed reservoir is a strong explanation. It helps explain why new comets can still appear, why many orbits do not look as if they come from a nearby disk, and why the gravitational edge of the solar system must be far wider than familiar planetary maps suggest. But a strong explanation still leaves a large gap. If such a distant, icy reservoir exists, those pieces of material could not have simply appeared there in a simple way. The early solar system was denser, hotter, and more chaotic than it is now. The material that formed planets, comets, and small bodies was initially concentrated closer to the Sun within a rotating disk of gas and dust. For some of that material to be sent out to orbits so wide that they are almost separated from the planetary region, there had to be a mechanism strong enough to throw them outward while still not completely freeing them from the Sun. That mechanism begins in a solar system very different from the stable image we know today. Before the planets had their familiar orbits, around the young Sun there was a disk of gas, dust, ice, and rock moving in chaos. Inside that disk, small grains collided, stuck together, broke apart, and then merged again. Over time, some regions accumulated enough material to become planetary embryos. Other regions were left with smaller fragments, like leftover raw material from a system still arranging itself. Those small fragments were not born at distances of thousands of astronomical units. In models of solar system formation, most of the original material was concentrated much closer to the Sun, within the disk where the planets were growing. To send an icy object very far outward, there had to be a force strong enough to change its orbit. Not a gentle push, and not a peaceful process. It required a gravitational encounter with much larger objects. The giant planets play the central role in that story. Jupiter, Saturn, Uranus, and Neptune were not just large planets sitting still on a map. In the early period, they were enormous gravitational masses moving through a sea of smaller material. When a planetesimal passed too close to a giant planet, its path could be bent strongly. One encounter could stretch its orbit outward. Many encounters could push that object away from the region where it first formed. Some fragments were thrown so strongly that they left the solar system entirely. Others fell back into the inner region or were pulled into a planet. But there was a group in between, far enough away that it no longer belonged to the familiar planetary region, but not fast enough to escape the Sun's gravity. They were placed onto enormous orbits, long, cold, and almost separated from the bright part of the solar system. That is how the Oort Cloud is seeded in many modern models. Not as a layer of material that had already been sitting at the outer edge from the beginning, but as material scattered far away during the process of the solar system stabilizing itself. Those objects may have begun near the region of the giant planets, then been pushed outward by those very planets. A distant structure like the Oort Cloud may therefore carry within it the memory of a chaotic period much closer to the Sun. This point also explains why objects in the Oort Cloud source are thought to be very ancient. If they truly are remnants from the early solar system, they may preserve material that has not been processed as much as matter on the large planets. But the evidence must be kept at the right level. Science does not yet have a sample taken directly from the Oort Cloud. What can be said is that long-period comets, when they enter the inner region, carry ancient icy material and their orbits suggest that this reservoir must lie very far away. In this picture, the Oort Cloud is not only the outer edge, it's like an archive of things once pushed off the main stage. The large planets formed, claimed material, changed the orbits of smaller fragments, and then left behind a region that is almost invisible. But once those objects had been sent so far away that they were held only by a very weak gravitational thread, the solar system was no longer the only force touching their fate. At that distance, the objects thrown far outward no longer exist in an environment made only of the Sun and the planets. Near the inner region, the Sun's gravity dominates almost everything. The planets can alter the paths of small bodies, pull them into resonances, throw them outward, or hold them in familiar orbits. But the farther out one goes, the weaker that dominance becomes. The Sun can still hold small pieces of ice, but the gravitational thread becomes much thinner. An object in the Oort Cloud does not need a direct collision to change its fate. It only needs a small pull, repeated for long enough, or one disturbance precise enough. In a place where orbits have stretched to thousands or tens of thousands of astronomical units, even a very small change can accumulate into a major difference. One of those sources of disturbance comes from the galaxy itself. The solar system is not standing still in empty space. It is moving around the center of the Milky Way, passing through the gravitational environment of a much larger structure. The gravity of the galaxy does not pull objects in the Oort Cloud in a strong and sudden way like a giant planet. It is more like a very weak background force, capable of gradually changing the widest orbits over extremely long periods of time. That influence is often called the galactic tide. In the problem of dynamics, it matters because the Oort Cloud lies where the Sun's hold has grown weak. An object there may still belong to the Sun, but it is no longer controlled by the Sun as completely as a planet is. Its orbit can be slowly pulled off course until its closest point to the Sun drops lower. When that happens, a piece of ice that once lay still in the distant region can begin its journey into the inner region. Beyond the galactic tide, there are also passing stars. Most passing events do not create anything obvious. There is no scene where a star sweeps by and immediately throws a swarm of comets into the solar system. The reality is quieter and more subtle. A star may pass at a very great distance, but for objects lying at the gravitational edge of the Sun, that small pull can still shift some orbits. Not all of them, not immediately. Only a small fraction in a system so vast that major changes often begin with very small shifts. This is what makes the Oort Cloud different from more familiar regions. It is not only a place where the Sun keeps remnants of the past. It is also a place where the solar system makes contact with its surrounding environment in a way that is hard to see. The icy objects there both belong to the Sun and remain sensitive to the galaxy, to other stars, and to pulls that would be almost insignificant in the inner region. A long-period comet appearing in the bright region may have begun its journey after a very small change like that. It does not require an explosion. It only requires its orbit to be adjusted enough that the distant piece of ice no longer continues to lie still in the outer region. From Earth's point of view, that comet seems to appear suddenly. In reality, its path may have been altered long before, in a place where the Sun still maintains control only through a weak and slow pull. Once the outside environment can touch the objects of the solar system in that way, the boundary between what belongs to the Sun and what comes from the space between stars is no longer completely clean. The Oort Cloud may not only preserve material thrown outward from the inside. Part of its story may have begun when the Sun was not yet as alone as it is now. That period pushes the story of the Oort Cloud farther back than the present stability of the solar system. Today, the Sun looks like a solitary star, moving through the galaxy with its planets, asteroids, comets, and pieces of material held by its gravity. But when it first formed, this central star may not have been born in an open region like the one it occupies now. Many stars are thought to be born in young star clusters, where hundreds or thousands of stars form from the same giant cloud of gas and dust. If the Sun was once in an environment like that, the space around it, when it was young, would have been much more crowded. Young stars could have passed closer to one another. Each forming star system had its own disk of material, its own planetary embryos, and small pieces of ice and rock scattered by growing planets. In a more crowded region, the gravity of one star does not act only on its own material. Close encounters could disturb material at the outer edges of young star systems, throw some of it outward, or in some cases, allow one star system to hold it onto material that once belonged somewhere else. This is not something that can be stated with certainty for each piece of ice in the Oort Cloud. No sample has been taken directly from that region to label its origin. There is also no way to look at a long-period comet and immediately confirm whether it was born around the Sun or around another star. What science can do is build models of the young stellar environment, calculate gravitational encounters, and see whether some material could once have been exchanged between star systems. That possibility makes the Oort Cloud stranger. If most of its material came from the early solar system, this distant region was already an ancient archive. But if a small part was captured from the environment where the Sun was born, it would not only preserve the history of the solar system itself, it could also carry traces of a young stellar region that broke apart long ago, where the Sun's sibling stars were once closer before each star followed its own orbit through the Milky Way. The important point is not to turn this possibility into a certainty. The Oort Cloud cannot be described as a reservoir of extrasolar material in a direct sense. The current evidence does not allow that. A more careful way to see its origin is as a story with many layers. The main layer comes from material scattered far outward by the giant planets. A deeper layer may be connected to the environment where the Sun formed, when star systems were still close enough for their gravity to touch one another. In that view, the outer edge of the solar system is no longer a clean dividing line between inside and outside. It is more like a mixed region of memory. Some pieces of material may have begun near Jupiter or Neptune and then been thrown far outward. Other pieces, in more cautious models, may carry traces of a stellar environment that is now gone. And at the inner edge of that distant region, a few strange objects begin to make the map harder to keep settled. Closer clues begin to appear in the region beyond Neptune, where the map of the solar system is no longer as simple as an icy belt lying beyond the last planet. The Kuiper Belt has its own structure. The scattered disk has orbits that are pulled much more strongly out of shape. Farther out are objects that are almost separated from Neptune's direct influence, traveling on long, cold orbits that are difficult to place into a familiar group. Sedna is the most striking example. When it was discovered, this body was much farther away than Pluto, on an orbit so stretched that one trip around the Sun takes more than 10,000 years. Sedna's closest point to the Sun is still more than twice Neptune's distance. Its farthest point reaches even deeper, into a region where ordinary planetary maps are almost no longer enough to explain it. What makes Sedna important is not that it proves the Oort Cloud has been seen. Sedna does not do that. This body is still too close compared with the outermost region usually associated with the Oort Cloud, and its classification still requires caution. But Sedna's orbit raises a difficult question. If Neptune cannot easily create that kind of orbit, then what force pulled this object out of the familiar region? There are several possible explanations. A star may have passed near the young solar system. The Sun may once have been born in a more crowded star cluster than the one it occupies today. Dynamical processes in the outer region may also have left objects on distant and detached orbits. Each possibility touches the same point. The outer solar system is not a map that has been locked in place. It still preserves traces of forces that acted long before humans began observing the sky with modern telescopes. In that picture, the Hills Cloud is often mentioned as an intermediate region. If the outer Oort Cloud is the extremely distant layer, almost completely beyond direct observation, then the Hills Cloud is imagined as an inner region, possibly denser and possibly able to replenish the more distant reservoir over time. But this is still part of the model. No image shows the Hills Cloud as a clear belt. There is also no list of objects confirmed with certainty. In the same way, astronomers catalogue many bodies in the Kuiper Belt. Sedna and similar objects make the story deeper, not simpler. They do not replace the evidence from long-period comets. They also do not erase the distance between what is observed and what the model infers. They only show that the transition region between the Kuiper Belt, the scattered disk, the inner Oort Cloud, and the farther part may be far more complex than a neat dividing line. These closer clues therefore still cannot close the case. Sedna may say that the outer region was once affected by strong forces or ancient gravitational encounters. The Hills Cloud may explain how an inner reservoir feeds more distant comets. But the largest Oort Cloud still lies beyond direct confirmation, while the known objects only touch the inner edge of the problem. At that distance, each new point of light does not make the darkness disappear. It only shows that the darkness has structure. And while telescopes are still searching for more distant objects like Sedna, another group of human witnesses left the planetary region long ago, flying in a direction that no one could call fast when placed beside the true size of the Oort Cloud. That group of witnesses was not launched to search for the Oort Cloud. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, and later New Horizons all began with goals much closer than that. Some spacecraft were sent to the giant planets. Some flew past worlds that had never been seen from close range. Some expanded the map of the outer solar system with data no one had ever had before. But after completing their main missions, some of them kept flying outward, not turning back, not stopping, only continuing on the inertia given to them from their first launch. In the imagination, that sounds like a straight journey to the final edge. But the true size of the Oort Cloud makes every sense of speed become smaller. Voyager 1 is one of the farthest human-made objects ever to leave Earth, but even that spacecraft has not yet reached the inner region of the Oort Cloud. In the way NASA often describes the scale, Voyager 1 would need about a few hundred years to reach the inner part and tens of thousands of years to pass through that entire vast region. That number places humanity on a very different timescale. A spacecraft can cross the orbits of the planets, pass through the heliopause, and enter the interstellar environment, but before the Oort Cloud, that journey is still only the first part of a much longer road. Not because that technology is small in an ordinary sense, it is small because the region that needs to be explored is too wide, too sparse, and too dark for a flyby to become a map. The quietest thing is that when those spacecraft reach distances related to the Oort Cloud, they will almost certainly no longer be explorers sending data home. Their power sources will decline. Their instruments will age. Their signals will weaken with distance. A spacecraft can still continue drifting through space, but no longer have the ability to describe what it passes through. it becomes a human-made artifact, carrying Earth's memory, flying into a region where it no longer has enough of a voice to describe it. That is the limit that keeps the Oort Cloud outside a truly direct exploration. The spacecraft that have left the planetary region prove that humanity can send its objects very far away, but they cannot replace a mission designed specifically to search for small, dark pieces of ice at enormous distances. A journey through a region is not the same as a survey. An object flying in silence cannot replace a map with enough data. While no mission has yet directly opened that region, the Oort Cloud still stands at the boundary between what has been inferred and what still cannot be seen. Long-period comets have carried its traces into the bright region. Humanity's farthest spacecraft only remind us that distance is still part of the mystery, and the remaining gaps must be filled with orbits, time, and data, still insufficient to turn the dark region into a familiar place. Those gaps are the most honest part of the story of the Oort Cloud. This is not a place that has already been fully seen and is only waiting to be named, nor is it a vague idea kept alive because it fits the imagination. The Oort Cloud sits between two far more uncomfortable states. It has not appeared in a direct image, but the traces leading to it are too consistent to ignore. What is observed is still long-period comets. They enter the inner solar system on wide, tilted orbits, arriving from many different directions. They do not behave as if their entire source lies in a flat belt near Neptune. Each time a comet like that appears, the visible part is only the final moment of a journey that has lasted through darkness. The more important part lies in the path it leaves behind in the data. From those paths, scientific models build a distant, cold and sparse reservoir where icy objects can be held for a very long time. That source may have been seeded in the early solar system when the giant planets scattered material far outward. Later, at the fragile gravitational edge of the Sun, galactic tides and passing stars could adjust the orbits of some icy fragments, causing them to fall back toward the bright region. But the uncertain part remains large. No one knows exactly how many objects the Oort Cloud contains. No one knows the true mass of this region. Its boundary is not a sharp circle on a map. Sedna and other distant objects may suggest that the outer region is more complex than once thought, but they have not closed the case. The spacecraft that have left the planetary region have not been able to do that either. When they reach distances related to the Oort Cloud, most of them will only be silent artifacts of a civilization that once tried to see farther than its own abilities allowed. What makes the Oort Cloud special is not that it has been proven in the familiar way. It is special because it forces science to work at its own limits. There is no surface to land on. There is no clear photograph to zoom into. There is no directly confirmed outer Oort Cloud object to point to and say that this is the final evidence. There are only orbits, time, gravity, and comets, appearing like scattered messages from a region too distant to speak for its own existence. In that place, the solar system does not end with a wall. It fades into darkness, into weak gravity, into orbits longer than human memory. Eva, the Oort Cloud, if it is as the current models suggest, is not the pre-drawn outer edge of the Sun's home. It is the part of the map still being written by objects returning from a place almost impossible to see. The Oort Cloud leaves behind a quieter feeling rather than a complete answer. There are regions humans still cannot see directly, but can still trace through motion, through orbits, and through comets that only appear when they enter the bright region. Thank you for staying with Astrexo until the end of the journey. If this video helped you see the solar system in a wider way, please hit like, share, and leave your thoughts below. See you again on the next journeys, where each small trace can open into a much larger dark region.